刚性啊，是 Hello, hello, testing. Hello, 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 hello. Okay. Is the black box here visible or not? Okay, okay. Okay, so I think we should start now. Okay, good morning to everyone. So let's recall what we have done yesterday. So yesterday we introduced statement, right? Statement. So what are statement in mathematics? Yeah. Yes. So we only interested in sentence that are either true or false, but not both. Okay. If it is both true and false, then we will get a contradiction. Okay, we don't like contradiction because it's false always. Okay, and the next part we introduce statement with variables. Okay, there's some variables inside my statement, and we can quantify them. Right, there are three quantifiers we have. So what are the three quantifiers we have? Hmm? Universal quantifier, and then uh, existential, and then uniqueness. Right, uniqueness. Okay, so one example I gave in class yesterday, right? So the fruit is sweet. Right? So fruit here become the variable. So what kind of fruit you are talking about? Right? Is it all fruits are sweet? Huh? No. Why? Why did you say that it's false? Lemon is not sweet. Okay, lemon is not sweet. Okay, good. So this one false. So there's this. So there is this a sweet fruit. Right? So this is this true or false? Is this a sweet fruit? Huh? True. So find me a sweet fruit. Watermelon. Okay. Sure. Watermelon is sweet. And that is this a unique sweet fruit? True or false? False. Why? Show me. Banana also sweet. Right. Banana is different from a watermelon. Right. So there are two sweet fruit, but they are not the same. Okay. 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 So this is what we have done yesterday, basically. So you see, to decide whether this is true or this is false, you need to prove it. You cannot just say, I believe it is true. I believe it is false. Okay, you need to prove it to me. Okay, for example, how you prove the fruit is sweet. Bring one watermelon and let your friend eat it. Is it sweet or not? You decide. Right. Okay. So we need to prove. Okay. So to show that a statement is true, we need to prove. So today we will talk about introduction to proofs. All right. So yesterday we defined what is definition, right? Definition is a statement that is always true, okay? To explain precise meaning of some word, symbol, concept, okay, to avoid confusion. And next, we will introduce axiom, okay? Axiom or postulate. And so these are the statements assumed to be true, always, So the famous axiom we have in the mathematical history is like the 5 geometry axiom by Euclid. Right? So the Euclid geometry axiom, okay, which talk about a definition of circle, parallel line, and so on. Okay. Next, from this axiom or postulate, we can deduce a series of theorems, okay, or propositions or claim. So what are these? So these are all statements as well that can be shown as a consequence of the axiom. Okay. So these are the properties that are appears as a consequence of axiom. Okay, so what's the difference between these three words here? Theorem, proposition, and claim. Okay, so basically, this three words differ by their implication. Okay, how important they are. So it depends on their implication. Good morning. Again, depend on their implication, right? So typically, theorem has more influence than a proposition and more influence than a normal claim. Okay, but basically, they are proven statement. And next, so how we show that they are true? We use proof. So what is a proof? So a proof is a valid argument that establish the truth of a theorem. Okay. So this is quickly recap what you have done in your discrete math. Next, we introduce lemma. Okay. Lemma is also a proven statement, but I want to single out this lemma because it is an auxiliary theorem proof beforehand. For the proof of another lemma. Sorry, for another theorem. Okay, so for example, in a mathematical history, we have John's lemma or Gauss lemma. So when they are trying to prove a statement, right, a theorem, but in the process of proving, they reach another difficulty, right? So they would need to prove that statement first before you can prove the original statement. And then this middle statement will become the lemma. So you see, this lemma, these two lemma are attached to two mathematicians, Jones and Gauss. Okay, so maybe you can do some research on Jones lemma or Gauss lemma. So what are the original questions they are interested in? Okay, why they need to prove this lemma first? Proving this lemma will lead to what? Big theorem. So this is two possible project you can look for. Actually, Gauss lemma refers to a lot of different versions. Okay, and typically when they attach names to this lemma, right, meaning these lemma are quite useful. It's very useful. Okay, It's quite useful. Okay. And I put a remark here. What's the plural for lemma? Anyone know? Plural for lemma. Huh? Want to guess? Yes. Any guess? Lemma. Any guess? Lemmas. Okay, lemmas accepted. There's another version you can call it lemmata. Remember, there's a similar word in the biology. Stoma. Stomata. Okay, yeah. Lemmata. Or lemmas. Lemmas also good. Okay. Next. So we have a corollary. So what is a corollary? Okay, corollary is also a proven theorem, but why we need to create this extra word here? So a corollary is a theorem that can be established directly, almost immediately, okay, from a theorem with little or with no proof. Okay? So when you read uh, when you read um, the mathematical text, right, the references I gave you, they will have proposition, theorem, corollary. So corollary means it's very easy to deduce from the theorem. Maybe you just need to do some substitution. That's all. No technical skill involved when you need to prove the corollary. Okay. So if you think about how to prove the corollary, but you are get stuck, that means you are going too far. Actually, it's easy to deduce from the theorem. This is what meant by corollary. Okay, with little or almost no proof already. You just need to do some substitution. Okay. Morning. Yeah. Okay or not? Does it make sense? Okay, when you see corollary, it's just an easy consequence of the theorem above. Okay. Okay, so final terminology here is called the conjecture. Okay, what's the conjecture? This is a statement that we don't know whether it's true or not, but we guess that it is true. Okay, so a conjecture is a statement that is being proposed to be a true statement. I think it is true statement. Any famous conjecture, you know? You heard of any famous conjecture or not? Huh? You mean special relativity? Relativity? 相对论. Relativity is proven. It's already proven. Yeah, it's proven. But this one conjecture is not proven yet. But we propose it to be a true thing. Yeah. Four color conjecture. Yeah. Yeah. That's right. I think four color conjecture is it proven in a lot of way already now? Not yet. Okay. Yeah. So wait, let me put here. This is about graph theory, right? Yeah, there's a lot of attempt to attack this question from various way, but the first setup of this question is graph theory. It's kind of combinatorics, but people have been trying to attack this question from higher algebra, from topology. different way they approach this question here. Right. So let's make a quick summary here. So what have we introduced? So the upshot here is first, our mathematical system start with axiom or postulate or even definitions of word. Right. So these things are assumed to be true. Okay, we work in some setting. Okay, and then from this setting here, we can prove, we can do proving, and prove some lemma or prove some propositions, so that we can get a nice result. Okay, maybe it's our big theorem here. Okay, do some proof again, and maybe these theorems will lead to a lot of children, okay, corollaries, okay, with little proof. Okay, but if you haven't proven the statement yet, then these are just conjecture. There's a lot of conjecture in the history get proven wrong as well, right? So something that you think is true is called conjecture, but what you think is true might not be true. Okay, so conjecture could be wrong. It could be false. Does it make sense? No. So conjecture in Chinese is what? 猜想. Okay, so you just guess. You just think about it. You just think that it's true. Okay, but you need to prove it. It could be wrong. Okay, a lot of conjecture proven wrong. So I put here maybe true or false. Okay. So you should note that here, this definition axiom postulate is very important here. Because if we change another set of axiom or definition, then different theorem will pop up. Okay. So what mathematician thinks in true in one setting might not be true in the other setting. Okay. So what we mathematics do is typically we explore possibilities in various conditions. And this is what a real mathematician is doing. Does it make sense? Make sense? Okay. Okay, any question before we go to the next one? Yeah. Any standard for axiom? Of course, you cannot give a contradictory statement inside your axiom. Otherwise, maybe nothing exists for your axiom, right? So you need to have a consistent system for your axiom to work. Because if you have a contradiction, then you can prove everything, right? So you need to have a consistent system first. Yeah. Any other question? Yeah, this consistency of this mathematical foundation, right? It's typically done in a course called Foundation of Mathematics. Yeah, if you are interested. But there's no course yet here, right? But there's a course that dedicated to this mathematical logic. What we introduce here will be just those we will be using in the course later. Okay? It's just a basic. So you will frequently see these terms appearing in your reference book, textbook. So make sure you know what's the meaning, why they put proposition, why they put theorems, why they put corollaries. Okay, this is the main thing you need to get away. Okay. Any question before we proceed? Okay, so next we talk about methods of proof. Okay. So let's talk about proving implication, the conditional statement. So how do we prove a statement like P implies Q? Few ways to do it. Okay. Yeah. Ethan. Yeah, few ways to prove it. So first way you can do direct proof. So what is direct proof? So you simply assume P and deduce Q. Okay, so you have P in your working, P, and then you deduce Q. Sorry. Let's put the small Q. Okay. So you have P and then you deduce Q. So for example, let's prove if X is even, then 2X is even. How many of you took elementary number theory in the past semester? Can you see? How many of you? 1, 2, 3, 4, 5. 5. 5. Okay. You know how to prove this? So X here, we just consider integer. Okay, so assume proof. Assume X equals to 2k for some k in Z, right? Then 2x equals to 2 times 2k, which is even, right? Because 2k is in Z. So in this proof, what did I use? What did I use? Definition of even. So what's the definition of even? Can you guess from this proof? What's the definition of even? Yes. So if a number is an even number, it is a multiple of 2. Okay. So I write s as a multiple of 2. I need to write 2x as a multiple of 2 as well. Okay. Okay. So in fact, I can modify this statement, right? If s is odd, so then it's not the n. Then 2x is also even. Right? So no matter x is even or odd, 2x will be even. Yeah, because 2 already give me the multiple of 2 part. Okay, so this is a typical direct proof example. Right? So you assume P, again, and then you deduce Q. Assume P and deduce Q. Okay, right. So next, sometimes life is not that direct. So we can use proof by contradiction. So contradiction, there's one advantage of contradiction. It gives you extra condition on it. So what does contradiction do? You still assume P is true. but you assume Q is false as well, or not Q is true. Okay? In other words. And then you arrive at a contradiction. Okay. So what kind of contradiction you can get? For example, you arrive at P is false. But you assume P is true. But P cannot be true and false at the same time. Okay, so let me make a summary here. So you assume P is true, not Q is true, but you deduce not P is true. So you have P and not P in your system. Okay. So when I write here, these all things mean true, true, true. Okay. Does it make sense? Okay, you assume P is true. Okay, your assumption is true. Your result is false, but you get your assumption is false again. Okay, so you have P and not P lies inside your system. So maybe give some example. How about try this? If K is even, then K plus 1 is odd. I prove this by contradiction. So what do I have to do? Assume P is true. So assume K is even. And K plus 1 is not odd. Okay, meaning it is even. And then I have to reach contradiction. So meaning somehow I need to get K odd. Okay, can I get K odd or not? So let's try. Since K plus 1 is even, what can I do? I can write K plus 1 equals to 2 times sum M for M in Z. And then I need to get a statement about K, right? Here, this equation here is almost something about K. So what can I do? Let me call someone. What can I do? I forget to bring my attendance sheet. Who is the one sitting beside Wasabi here? Sydney. Okay. So what can I do to this equation to get something about K? Yes. So I take one from both sides. Okay. I take one from both sides. Is this about odd number or not? What is odd number? What's the definition of odd number? That one is not very useful, right? So let me write a number x is odd if there's this k in z such that x equals to 2k plus 1. We are 1 away from the even number, right? Okay, you are 1 away from the even number. But you see, if I define this way, right? This 1 here is a plus 1, but here is a minus 1. So what can I do? Assuming it's k, okay, m is k. No. We already used k, right? We cannot reuse the symbol. So what can I do? I just push. So there are two multiple of m, right? So what can I do? I just push 1, 2 out of the 2m. So what do I get? N minus 1 plus 2 minus 1. Right? Then in this way, 2 times n minus 1 plus 1. At the same time, where n minus 1 is still in. Yeah. Okay. So in this case here, means what? K is odd, which is a contradiction because you will assume K is even just now. K cannot be even and odd at the same time. Okay, we prove that our assumption is false. So you see, compared to the direct proof, we have extra condition, not Q. Okay, no, we have extra condition to help us. And the third way is proof by contrapositive. So yesterday we learned that P implies Q is logically equivalent to not Q implies not P. Okay, so what we're gonna do for proof by contradiction is we first assume Q is false and deduce that the assumption P is false as well. Okay, so if I make into the table, so first we have not Q and then we deduce not P. Okay. So similarly, I claim that this contradiction proof here can be modified into a contrapositive proof. Okay. So meaning I assume K plus 1 is even, I prove that K is odd. Okay, I let you discuss with your friend in 5 minutes. Discuss with your friend. Write down a contrapositive proof for this statement here. If K is even, then K plus 1 is odd. Yeah, try discuss with your friend and then see how to modify this proof into a contrapositive proof. Yeah. Okay. Yeah, discuss with the one beside you. Turn this contradiction proof into a contrapositive proof. Okay, done? Done. So how done or not? Done. Okay, let's try. So how done, right? So how do you start the proof? Assume k plus 1 is even. Okay. So let me bring the statement down again. Okay, assume k plus 1 is even because you want k plus 1 not odd. Okay, then for some m in Z, sure. Next, move the 1 across. Okay, so what I prefer is we add -1 on both sides. You will soon see that this is called a cancellation law. Actually, you are not moving 1 across, but you take 1 away from both sides. Okay, then you want to show that k is odd, right? But is k odd now? Not yet, right? We need a +1, but here is a -1. Then what to do? Same proof as before, right? We can pull a 1 out. Pull a 2 out. Then we get 2 times m-1 plus 1, which is odd. Okay. So can you see the similarity between contrapositive and contradiction proof here? What's the difference? What's the difference here? What's the difference here? What's the difference between these two proofs? Quite similar, right? The middle part here is exactly the same. But what's the difference between these two arguments here? Yeah, for contradiction, we have a extra condition that P is true. Okay, we have an extra condition. And then something gets wrong because we have a contradiction. Okay, but in the contrapositive, we straight away get not P. That's all. Okay, we don't need to compare to P. Does it make sense? Okay. Yeah, sometimes the contradiction proof can be turned into a contrapositive proof. But sometimes contradiction doesn't lie with the assumption, maybe lies with the consequence of the assumption. Okay, so it still depends what statement you want to prove. Okay, you can pick any method of, you can try any method of proving. Okay, to give you a sense how to prove a statement. Okay, no? Okay, so this is typically the three three type of proof you can try. Okay. Any question regarding this two proof? This three proof method. Okay, if not, let's go to the next one. So how about proving equivalence? Okay, so this is to prove if and only if statement. Yeah, I give you this kind of question in your assignment, in your calculus 2, right? Prove two definitions are equivalent. So what do you need to do? You need to do two direction, right? So you need to prove P implies Q and Q implies P, right? So what are the possible way you can do to prove this? What kind of combination of proof you can do? So either you can use direct proof for P implies Q, or you can use the contrapositive proof on Q implies P, or you can use contrapositive for P implies Q, and then put a direct proof for Q implies P, or you use contrapositive for both. Okay, these are all logically equivalent. So the easiest way to attack a statement is to try with direct proof. But if direct proof is too hard or you have less information, then you can use contradiction. Because in contradiction, you have one more information, which you can assume not Q is true. Okay, assume your result is false. Right? Can you reach contradiction or not? If you can reach, then you can prove the statement. Okay. You know why contradiction work? Why can you assume P true, assume not Q is true, then you get not P, then this whole thing proves that the statement holds. You know why? You know why? Why it works? Why doing this will prove the original statement? Why doing this prove the original statement? It just says that contradiction, right? So why contradiction will prove the original statement? Why Ethan? Sorry? If P, then Q means what? If P is true, Q have to be true. So what does contradiction give you? Something true. If P is true, not Q cannot be true. Otherwise, you reach a contradiction. So Q must be true. Then I prove P is true, Q is true. Does it make sense? Does it make sense or not? Okay. Okay. You see, if P is true, not Q is true as well, then I reach a contradiction. Meaning what? Meaning not Q has to be false, which means Q is true. So P true, Q true is if P then Q. Yeah. How? Uh-huh. If P is true, mm-hmm, mm-hmm. Yes, yes. Not P is true. What do you mean? Not P is true, not Q is true. Say again. Uh, mm-hmm, mm-hmm. Yeah, sure.
Instead of saying Q is false, can I say P is false?
Can you say that P is false? You can, but like what we discussed last time, right? If P is false, right, there's nothing to prove about this statement. The whole statement is always true. False implies everything, yeah? Yeah, not P is not the only contradiction you can get, yeah. If you can use P, maybe deduce some R, and then you get not R, then then you still contradict not P, right? Because not R implies not P. So you can always get back to P. Yeah, you can always get back to P. Mm. Unless sometimes the statement could get a bit tricky. If K is even and something else. So if P, so let me show you. So this example maybe get somehow trickier. So maybe we could have if P and R, then Q, right? Something like that. So you assume P holds R holds, right? And then you assume dot Q. Maybe you can get contradiction on R, something like that. Okay, if you have more condition. Maybe if k is even and it is divisible by 4, and then something happen. Okay. But contradiction must be drawn from the assumption or the consequence of the assumption. Okay. 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 3 more slides before we take a break. So next, okay. Here we talk about that involve quantifiers. So we have a few statements. So how about to prove for all x, px? Okay. So you want to prove something is true for all x. So what do you do? Okay, you want to prove some statement is true for all x. What do you do? Yes. Okay, so you take an arbitrary x. Any x, no condition on x. No extra condition, I would say. Again, no extra condition on x. Then you prove px. Actually, what we have discussed just now is this kind of statement. So for every x, so for every k, k is even, then k plus 1 is odd. Okay, so what we do here, we didn't put extra condition on k. We just assume any k. Okay. Okay, and then next, how to disprove it? Okay, how to disprove it? Yesterday we discussed about this, right? How to disprove this kind of statement. Something is true for everything. Find something is wrong. Just find one is enough. Okay, find and counter example. You say that it works well with everything. Okay, find one example for them, okay, to show that it's wrong. Okay, 3. How about proving the existential quantifier? There's something that px is true. Okay, how to prove it? Roland, how to prove? I said there's something that px is true. So how you prove? There's something. So you said there's something, right? There's some fruit is sweet. So you need to, what do you need to do? How to prove your statement? How you convince people? You said there's some fruit is sweet, right? I don't believe you. Can you prove to me any fruit is sweet? What do you do? Ah, ah, one fruit not sweet? No. So the statement you want to prove is there is a sweet fruit. But I don't believe you. Yes, just take one X is true. Okay, just find me a sweet fruit. Is enough. I don't need to show you every fruit is sweet because I said there exists some sweet fruit. I didn't say all fruit is sweet, right? So just find me one X such that PX is true. Okay, so how to disprove this kind of statement? Okay, let's say I don't believe you. Okay, there's a sweet fruit. So I show you that I give you any fruit, right? And then I will disprove it. Okay. None of them is sweet. Okay, for example. Okay. 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 So before we end this part, or actually there's one more one more proof is called proof by induction. We will meet this again when we introduce natural number. So what does proof by induction do? You have a base case. Okay, and then you have an inductive hypothesis and inductive step. So I give you a very simplified picture of this proof by induction. So proof base case is assume, not assume. So prove that uh, n equals 1 is true. Okay. So inductive hypothesis says that assume n equals to k is true. So what is true? So it's a statement on n. Okay. Assume when n equals to k, Pn is true. And then inductive step is to prove P k plus 1 is true. So this is a simplified picture of proof by induction. We will meet this again later when we introduce a natural number. Okay. Have you guys been introduced to this kind of proof? Okay. Okay. We will meet this formally again later. I just want to give you a picture first. Okay. So before we take a break, so there's some vocabulary you can refer to. Okay. Later when you do proof writing and also your project. Okay. So now you enter second year already, right? I hope your writing will be more matured than your calculus 2. Okay, so please use a standard mathematical vocab. So normally what kind of vocab we will use? So you will typically see suppose something something, right, is true, or given an arbitrary x, given something, or you assume something, or let x to be some integer number. And since something is true, what will happen? Or observe that we have this or that, right? And similarly, we can put not that. Okay, remember that, right? And for contradiction, we will have suppose for the set of contradiction. Okay. When you know you want to do a contradiction, right? It's better you write that suppose something for the set of contradiction, because normally this kind of assumption is quite abnormal. Because when people read your text, right, you say suppose this is true, but sometimes that condition will look very weird or abnormal at first. It is weird because you want to do a contradiction. Okay, so people will know you want to do a contradiction. That's why you assume this kind of a weird condition. Okay, so it's better you write down you want to do a contradiction. Or similarly, you can write that suppose on the contrary. Okay, these are all for contradiction. Contradiction proof. Okay, suppose. Okay, SP is suppose. Okay, so some pronouns you can use is I already mentioned last time. We say we or once. Okay, or the reader. Left to the reader to do the reader. Okay, and then some connective word you can use is like so, then, thus, hence, therefore, right? Whence, here, but. It follows that. Okay. Consequently, subsequently. Right. So you see, there's so many connective words here. Don't keep on writing then, everything then. You see, you can use then, thus, hence, so, therefore, different word, right? So don't repeat, okay, everything then. 然后, right? Okay. So there's so many different vocab you can use here. Okay, what else? Let me see. Okay, there's more, so something like next. After that, moreover, beside, furthermore. On the other hand, okay. On the other hand means it is continuous, but it's on the how to say? It's on the parallel side. Okay, it's on the parallel side. On the other hand, right hand, left hand, right. On the other hand, and two words that abused by mathematician is clearly and obviously. Try to avoid these two words in your beginner proof, right? You don't want to skip too many steps. But you will typically see this in a textbook or classical book. You know why they use these two words? Because they think that the step is too easy for them. They can straight away construct in their mind. Okay? Yeah. So whenever you see these two words, it should be something easy. Not easy, but it's a routine. You have to do one. Okay, it's not something special anymore. It's just some calculation you need to do. Clearly, this is true. Okay, there's just some calculation you need to do. Okay, when you see this in the proof writing. But try to avoid these two words in your beginner proof. Okay, unless it's really obvious. Obvious from definition, I would say. For example, I give you an example where I can put obviously here. So let's come back to this proof here. So I said assume k plus 1 is given, then k plus 1 can be written as multiple of 2. Okay, and then I do manipulation to this, and then I get this plus 1. And then I can say, which is obviously odd. Yeah, because it's from definition, obvious. Which is clearly odd. Okay, I put here, which is clearly odd. Which is obviously odd. Okay. Which is blatantly odd. 太直白了 blatantly 超直白 okay then blatantly odd okay 抽到什么梗啊okay yeah okay blatantly odd right so from definition then you can use otherwise try to avoid these two words in your beginner writing. Okay, last few is you can use I think you can always see me using such that, right? Such that something so, where something so, which is what, okay, which is odd, which is even, which is divisible by what, or when something happened, or whereas is like but, right? And that is. Okay, so there's so many vocab here. Please don't repeat. This is what my English teacher told me. Okay, don't use a repetitive word. Let's try to look for a different vocab here. Right, so this is a list you can come back and refer next time when you want to want to write a proof. Okay, any question before we take a break? Any question before we take a break? Any question? No, if not, we will come back in 10 minutes. So let's return at 10:09 and we will do set theory. Yuan, can you come here? You enroll in the school. 你在我们班里面，你在我们班里，你没有 去考的时候还是这边？
我在
你在玩吧？OK，对，你昨天没有上？
昨天没起来床，
OK OK，
真的太香。
哎，你这学期拿什么课？你这学期拿什么
我拿了跟看 list，
？OK，所以你基本上还是跟这一班一样。OK OK，嗯 OK，就我们的这个 setup 跟 AWS 基本是一模一样，因为它是无 credit，所以我们还是会有 project 跟 presentation。OK，我放在那个幕的右下。
我 check 我还上不多。
你 check 一下。
OK，
啊，之后我会再 update project 的东西。
可能，这个就是那个是等下为什么是等，然后是因为我不确定对不对啊，那你可以在上课时候讲一下，
讲什么？
就是为什么那个是assistant，或者是为什么用的设备会是 assistant？
什么？
I mean like 就是
你
小
说
小 step。
为什么？还有
还有就是刚才你用这个是不是我觉得很多这个是
哦，
然后就是I mean like
愿景你知道吗？
我是
你知道就 OK。
然后还有
如果没有人提出来，我也不知道他们知道不。
OK 还有就是这个好像比如说 P index 因为我曾经会 confuse 这样的东西，就是它其实是可能这里像这个是代表，这个是它的一个 statement，所以我对，但是 I mean option 其他会怎样？
哦 OK， 愿景你不 confuse 就可以。
还有就是那对嘛，是不是？
对。
该会是选那个 set theory 的那个 option。
对呀，
但是我不确定啊，
不知道是谁。
但是
你说你是说会选 set theory 方向的人
对对
？OK，
你是他们那个国家是他选那个人，然后过后
你可以都可以，
还是
但 as long as 你是在 describe 一个人做出来的一个 theory 就可以了。
还是你是指要去找那些 theory 开始是那一出来，然后过
都可以，就是因为我 in the end 我要的东西就是我这个人会 come out 我这个 theory and then theory 的 impact 是什么，就这样，这样 fit 这样，透过人去 study 那个 theory。
然后是指可能要写 essay 什么多少面什么讲。
有我全部 list 在里面，我就没，但是我慢一点再会讨论细一点。But so far 我有 list 在里面。
Okay, let's return. Okay, so I'm not sure you have seen or not, the class team chat has been set up, right? Basically, you can ignore my presence there. You can do whatever you want. You can informally discuss class material or related to class material stuff inside there, including your well-being, right? So the moderator will be Jingsen and Seng. So if you have anything, right, you don't want to talk to me directly, you can talk to them first. Okay, you can talk to them and then they will let me know, and then we will try and figure out if you have any problems. Okay. Does everyone aware of that team group chat or not? Yeah, you can speak there. You can ask your friend, hey, you know this or not, you know that or not. Do you understand what Kisan said today? What Kisan teach today, I don't understand. So you can discuss there, and then if there's problem that you cannot solve among yourself, and then you can bring it to me. Okay, no? Yeah, it's okay. You can just do a formal discussion then, informal discussion. Okay. So Han we asked about why the De Morgan laws for quantifier is true. To prove this, we don't introduce the tools. I think the tools that need to prove this is the universal generalization and something specialization, existential specialization, because you want to attach quantifier to a statement. But I can tell you why is this, how to say, why does this make sense? Okay. You want to show that there exists something, that something is true. How do you prove the person that that's wrong? If a person tells you that there's something such that PS is true, okay, you want to prove him wrong, what do you need to do? Whatever thing he finds to prove PX is true, you prove that it's wrong. And you prove that it doesn't hold for anything. Right? So that you cannot find anything to prove that it is true. Does it make sense or not? Anyway, does it make sense?
I mean, how just the existential and the
No, you cannot just talk about existential and you cannot just talk about quantifier itself. You need to talk about quantifier with a statement. Only this quantifier will make sense. Otherwise, it doesn't make sense. Mm-hmm. Mm-hmm.
My idea is like either 1, 2, or 3, or can be by that everything can be classified in the existential. I mean, like it's some sort like how to say, or I don't know how to explain.
Quantifier need to come with a variables. If there's no variables, quantifier doesn't exist. It's necessary. It's necessary. Otherwise, what's the use of the quantifier? It cannot be a standalone thing. There exists. What? It's not a sentence. There exists something such that we need to make a statement to it. Yeah. We negate a statement. We don't negate a quantifier.
Yeah, I mean, and this and the universal, we cannot like three, like we can put like there are 3 x in the is true for PS, and then there is 4 x is true for PS. Or no,
I don't get what you saying.
I mean, I see.
But do you get what I say or not? You get what I said? You cannot negate quantifier. You negate a statement. Quantifier is not a statement. Yeah. Okay.
For example, like x equal to 1,
Mm-hmm.
and when we negate it, it becomes x not equal to 1, right?
Sure.
So if for the existential is like it can be either 1 or 2 or 3.
Wait. What do you say? What are you saying? So x equal to 1, right? So what quantifier you want to put here?
You don't have.
I don't care first, okay?
Yeah.
Then what do I do?
If you negate it, it is not equal to 1, right?
Sure, and then
Some sort of classification, you know.
classify what?
Either x equal to 1 or x not equal to 1.
Sure.
All the
True and false, right? That's
Yeah,
why, yeah. And then
So can the existential and the universal span all the possible?
no, they are different. No, they are different. For all is true for everything. There is just, I mean, at least one thing is true.
Let me explain how I think why the negation of existential is for what I understand is like this. Existential is like it can be 1x is true for PS, or 2x is true for PS, or 3
There exists some x.
Yeah.
Okay.
Some is when we say some is like 1, 2, or 3 or more identity, right?
Just more than one.
Yeah, more than 1.
At least one.
So, but we keep continuing like existential, we cannot reach all number, right? We
Cannot.
All number, right?
Might
So
not.
if we cut out, so the negation is like negation is like you can do like the existential and the universal is like can help us to describe all the possibility.
What kind of possibility you want?
All the domain. It's like counting.
Maybe try and formulate your question properly again, then we will discuss again. Try and formulate your. Yeah, of course you are not sure. That's why try and formulate your problem. Try to write down and then ask yourself, does it make sense or not? You said you see now when you talk, right, even yourself doesn't make sense of yourself.
No, I mean
right?
like I can imagine it, but has to find something.
Sure. You have to find it. Yeah, you cannot make me find it, right? You have to find it.
For example, we want for example the set of I mean maybe natural number from 1 to can be larger and larger to infinity, right? If we existential only has the existential quantifier only, then actually we cannot say that the one statement PS is true for.
Sure.
So yeah.
Not sure what you want. You haven't say what you want. You say classify. I don't know what you want to classify.
What
Right.
I mean is like there are some reasons that I think it's similar to just now I say the x equal to 1 and x not equal to then all the
Yeah, sure.
the extension and the universal is some sort like that.
No, they are different. They are not like complement to each other. They are not kind of complement. They are quite different. You see that the way we prove they are true is quite different. They are not kind of complement to each other. I don't know in one sense. Not in any obvious sense, at least I see.
Want to use the universal generation to what?
Yeah. To prove this, you mean to get this why negate existential quantifier become a statement on universal quantifier. So you need to come with a PX, I mean. Okay, otherwise you cannot just negate a quantifier, no. Because negation we define on statement, negation of a statement, but quantifier is not a statement. You cannot just negate quantifier. Okay. Yeah. Okay, you can try and think about it again and try and formulate. Try and write down what you are saying, and then read it. Does it make sense or not? It doesn't make sense. Think again what you want to say. Okay. Yeah, you can always bring back again. Try and formulate your question properly. It's okay because this is a learning process. Okay, everyone have to formulate their own problems properly, because this is typically the confusion you have in your mind. Why you cannot solve a problem? Because you cannot formulate your problems well. Okay, why you have this confusion? Because you cannot formulate your confusion well. Okay, that's why you cannot solve your problem. Okay, so formulation actually is a very big issue. Okay, in your daily problem. Yeah. Okay, so you need to formulate your question properly. Okay, so let's go into set theory now. So let's recall a bit. We've defined a set. A set is simply an unordered collection of distinct objects. And then it contains what we call the elements. But we also can get a simple set or trivial set, which we call the empty set, okay, or a null set. So meaning there's nothing there, okay, which we denoted by phi. Okay, is the set has no element. That has no element. Our definition of set allowed this, okay, an unordered collection of distinct objects. So maybe if you like, we can put here possibly empty. And we have so many sets, right? So how do we decide two sets are equal? Okay, two sets are equal if they have the same elements. Okay, if they have the same elements, then they are equal. Okay, and we will write A equals B. I think Hanwei has some opinion on this, right? He argued a little bit about axiom of specification with me. You can try and start a conversation in the chat. Ask them whether you know this something is true or not. Okay, see what people think about this. So basically, we say that two sets are equal. Okay, set equality if they have the same elements. Okay, very intuitive here. And next, we can talk about subset. So if a set is a subset of another set B, okay, or in another direction, we can write set B is a superset of A if for every element in A, okay, it is an element in B. Okay. Then we will write A is a C with a horizontal line, B subset of B, or B is a superset of A, okay, respectively. Yeah. So we can use this definition to say that two sets are equal. So definition 2 of equality of set A and B are equal. We will write simply A equals to B. Okay, if A is a subset of B and B is a subset of A. Okay, so not that I use the same equal sign for number. So in mathematics, you need to be careful when you see equal sign. They are equal as what? Okay, equal as number, 2 equals to 2. 2 equals to 4, false. Okay, 2 doesn't equal to 4. But here, you see, I put A here, put B here, I put equal. Equal as what? Equal as set. Okay, so how is it equal as set? You need to prove that A is a subset of B and B is a subset of A. Okay, so what does subset mean? You need to go back to the subset definition. You need to show that for every element in A is an element in B, and then take every element in B, show that it's element in A. Okay, so I put definition 2 here. You just see that this definition is the same as the previous one. Previous one says what? The two set have to have the same element. If you found that every element in A is in B, every element in B is in A, do they have the same element or not? They should have, right? You have to prove it. Let's try and prove it. Prove this equivalent definition. Okay, so I put the exercise here. I think I will do the proof. I will provide the proof later, but try and do that two definition of set equality equivalent. I'll provide the proof, but you try and do yourself first. It's just unraveling the definition. Okay. Okay, next. So this is about equality. Next. Let me see. Yeah. Okay, so how about we do one interesting proposition here? Well, proposition. There is exactly one set with no elements. You know what is it? There's only one set with no elements. You know what is it? Empty set. Okay, the empty set. Or namely the empty set. There's no second empty set in this world. There's only one in this world. So what do I need to do here? So exactly one. What is this? This is the uniqueness. Exactly one. One and only one. Okay. So I already give you the existential part, right? Existence. So we can take an empty collection of elements. Okay. How about the uniqueness part? How to prove uniqueness? How do you show something is unique? Maybe there's only one Lamborghini in this world. How you prove it? Huh? Suppose there's another Lamborghini, right? And then show that actually it's the same Lamborghini. Okay. So to prove uniqueness, right? Suppose there are two sets A, B with no elements. Okay. What do we want to show? We want to show that A is equals to B. So here equality as what? Iron rule. Here equality as what? As equality as what? Don't know. A and B is what? What is A and B? Set, right? So here equality as set. So what's the definition of equality as set just now I said? If and only if and only if what? You need to show two things. A is a subset of B and B is a subset of A. Okay, you need to do these two things here. Okay, so let's pick one direction to do. So let's do the first one. So let's do the first one. So what do I need to show? A is a subset of B. So I need to take element from A. Okay, suppose X is an element in A. Then we want to show that X is in B. Make sense? Is everyone following? Okay. Or equivalently is what? Equivalently. Or x in A. Okay, we want to show that x is in A implies x is in B. We want to show that this is true. Is this true or not? Is this true? Yeah, try and discuss with your friend. Give you 2 minutes. Is this true? If it is true, why is it true? If it is false, why is it false? So you need to decide whether it's true or false. You need to know about A and B, right? What any information about A and B? Any information about A and B? No elements. Okay. So is S in A works or not? It's always false. X in A is always false. Why? Yeah, A has nothing. So you cannot say there's something in A, right? So S in A is always false. Okay. So this part is always false since A is empty. Nothing in there. You cannot find things inside A. Does it make sense? Make sense? There's nothing in there. So you see, P implies Q, but P is false always. So the whole statement is always true. So which is, okay, I put here clearly false, clearly true. Since A is empty. Okay. So we have proven A is a subset of B. Okay, sometimes we say that this statement is vacuously true. Vacuously true. Because you come from a false assumption. Vacuously true. Okay. Does it make sense? This is a trick. This is a trick in analysis. So make sure you get this trick here. Okay, if you get something false implies something, then you will get the whole thing always true. So you could similarly show it for the direction for. So similarly, you use the same trick to show that B is a subset of A. Okay, does it make sense? So you swap the order of B and A, you use the same argument because B also have no elements. And then so B is a subset of A also would. Okay. Any question? So this is about uniqueness. So in AA, right, abstract algebra, you always map this uniqueness statement, argument. Sorry. Okay. So existence, uniqueness, proof. Okay. So let's see. Okay, so we will quickly define what is the union of two sets. Okay, and define what's the intersection of two sets. Okay. So let A, B be sets. Okay. So what's the union? A union B. Okay. The union of A and B is what? Okay. Is everything such that we use the set builder notation, X is in A or S is in B. Do you agree that we can build a bigger set using this? Do you agree that we can build a bigger set using the union operation here? Do you believe? What's that? You could potentially build okay, what do I mean by bigger set? Okay, very good question. It's like the number of elements inside there will increase. Yes, right. Okay, I can take this table, the student in this table, or the student in this table. Okay, as long as you are in one of the table, I take you in. Okay, although English is like or you cannot, you just pick one, but actually or for us is like we pick all of them. As long as one of them true is true. Okay, it's not just picking one here, but picking all of them. Okay, so this is a bit different from the normal English. Okay, next we define intersection. The intersection A and B. So the intersection of A and B is X has to be in A and X have to be in B. So this intersection, right, typically reduce number. Because why? You need to satisfy more conditions. Okay, for example, you have to be a boy that is less than 15 years old. Then you reduce the number. Okay, typically intersection reduces this number. Union increases in number. Okay. Okay. Next. For example, next one is the difference. Okay, the difference of A and B. Okay, so what's the difference of A and B? We will write it as A minus B. Right? So it's the set that contain elements. So contain elements is in A, but not in B. Okay. So write it as a set builder notation. A minus B is equal to everything, such that everything is in A and X is not in B. Okay. So so if you want to see it as a Venn diagram form, so maybe let me draw this. So A and B. Everything in A that is not in B, so it's here. Okay, so this is the difference between two sets. Okay, so also sometimes we will write A slash B. Okay, so I take A and then I remove everything that is in B. Okay, this is how you could think about it. Okay, I take the whole A and then I remove everything that is in B. So, for example, let me test you. If I take a Malaysian and then take away Australian, what do I get? If I take a set of Malaysian and then I take away a set of Australian, what do I get? Who said? Who? Chen Jack, you said Malaysian. Why? 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 Why you still get that Malaysian? Sorry? There are no intersection. So why are there no intersection? Why they don't intersect? Yes, so Malaysian only accept one citizenship, not dual citizenship. But Australian accept dual citizenship. But if you get find out in Malaysia, then Malaysia will renounce your citizenship. Yeah. Okay. So Malaysian take away, Australian is Malaysian. How about US take away Australian? There's a lot of US citizen went to Australia to work, especially my supervisor is one of them. So let's say I have a US citizen. So US citizen, they allow more than one citizenship. Australian also allow. So what's the set here? Okay, the people only have US citizen. So this set is actually non-empty. Okay. Okay, so let's see, 10:41. Okay, let's continue further. So next. I want to introduce a set. So last time we talked about universal domain and domain of discourse. So let's talk about universal set. Okay. What is a universal set? So it is a set that contains all objects under consideration. So if you consider, if anything under your consideration, you can just take all of them as your universal set. And often we will look at complement of a set. So when we talk about complement of a set, we need to know where the set lies in. So where is the ambient space? Where is the bigger set it lies in? So let U be the universal set, okay, and a subset of this universal set, okay. Then we can talk about the complement of the subset A. So typically we will write it as A bar, right, or AC, A superscript C, or the universal set slash out A, okay, those in the universal set but not in A, or U minus A, okay, just now we use this notation here. So it's the set, okay, what's this set here? So AC equals to X in the universal set, and then X is not in A. Okay, so for example, just give a very easy example. So let's say, what's the complement of a Malaysian male? What do you think? Malaysian female, huh? Okay. So Malaysian female. So in your mind, what do you think? What are you thinking? Actually, you set your universal set as Malaysian. Okay, if you include the international student, then you include everything that's not Malaysian male, but it's in your universal set. Okay. So yeah. So this complement really depend on what universal set you are talking about. Okay. Okay. So whenever people say complement of something, then you should ask what's the universal set you are talking about. Okay. Only that you will know what's the complement of it. Okay, we still have 5 minutes. So maybe okay. Any question before this set part, set theory part? No? Yeah. Mm.
The influence of A and B.
Mhm.
How about the difference between A and A?
The difference with A and A, what do you think? A take away is what? Empty cell? Yes. Huh? Yeah, this one. Yeah. So you mean you want to replace? So let me write. So A minus A, right? So X such that X is in A and X is not in A. Contradiction. Contradiction. So nothing satisfies this. So it's an empty set. Right, so that's why we introduce empty set. Empty set is a quite important set. So it's a contradiction here. Nothing will hold true. Okay, if it's nothing hold true, then nothing is in the set, then it's an empty set. There's only one empty set in this world. Okay, so you produce an empty set from something. Okay, so it's like, hey, you see, this look very similar, right? A minus A equals to empty set. 2 minus 2 equal to 0. 3 minus 3 equals to 0. So you see, the set operation is somehow behaving like a number. Okay. Yeah, so there's a higher structure hiding here, actually. And then this will lead to a category theory at the end. Okay. This is not coincident, this is not coincident. But there's a higher structure governing these numbers. Okay, before we end, let me show you something. Okay, let me show you something. So we are at the start of building numbers. Okay, so we want to build numbers now. So let's build numbers from scratch. Okay, we're gonna build numbers. So first thing we're gonna introduce is the piano axiom for the natural number. Okay. How do we construct a natural number? So our first axiom, we need to start with something. We don't want to deal with an empty set. We want 1 to be inside our natural number. Okay. And then we want to talk about equalities in this set. Okay, how do we talk about equalities? So this is somehow an equivalence relation. So in equivalence relation, you have how many property to talk about? Equivalence relation. Still remember? Forgot. You guys remember what the equivalence relation is? Relation. There's 3 property about equivalence relation, right? You need to show that it is reflexive, symmetric, and transitive. Why is it important? Because this is characterizing what is equal means. What does it mean by 2 things have to be equal? If you say you are equal to something, right, first of all, you need to equal to yourself first. If you are not equal to yourself, then something will be wrong with your equalities. Right? So let me put down this axiom. So for everything in my N, okay, I want to define the equality in net. So now I define equality in this number. Just now we have equality on set, but now we have equality on numbers. Okay. So for every X in my set, X have to be equal to itself. Make sense? You have to equal to yourself, right? If you don't equal to yourself, is what? You have 多重人格 already. Maybe you have schizophrenia. Right? And you must equal to yourself. Second, okay, if you have 2 elements in your set, if X equals to Y, then Y should equals to X as well. So there's no symmetric problem here. Yeah, if you are equal to Y, then Y is equal to you. It's symmetric. 4. if you have three things that are equal, so such that x equals to y and y equals to z, then x equals to z. Okay, so this is really an ideal case, right? This relation is really ideal. If you are equals to Han Wei equals to Jing Seng, then I am equal to Jing Seng. But unfortunately, maybe human relation is not like that. But this is really an ideal case. Because this relation is transitive. I can bring this relation on and on and on. Okay. So this is somehow how we build a community. Okay. There's another extra condition on equalities here, epsilon 5. Okay, so for every x and y in this set, we don't know what set yet, but in the set we want to build, if y is in n and x equals to y, then I want to make sure that my x is in n as well. Okay, so this s and n shouldn't be in n first. Okay. So if you found someone outside, okay, which is equal someone inside, then bring it in. Okay, it's in n as well. Make sense or not? Does it make sense? Okay, if you have any two things x and y, okay, let's say y, I already joined this program, okay, and then you see that x is equal to you, and then bring the x to join your program as well. Okay, so I need to construct my n. Okay, so this is about anyone using this class? Can we go a bit late? Okay, maybe I don't continue writing first. Let me show you the whole axiom and then we will come back again. So we have defined 1 to 5, okay? 1 to make sure that it's non-empty. 2 to 5, we want to build a natural number set, okay? Build a natural community. And then 6 to 7, we will build a function, which we call a successor function, okay? And then give property to this successor function. And then 9 is this principle of mathematical induction. So principle of mathematical induction comes from here. Okay, if 1 is in the set, for every n in my natural number, then if n is in the set, then Sn also in the set. Then this set will contain the natural number. And then 10 to 11, we will define what's addition in natural number. And then 12 to 13 will define multiplication. And then this whole set will build natural number. Next week, I will show you how we build this natural number. How we build out 1, 2, 3, 4, 5, 6, 7, 8, 9. And by this successor function, right, very important here, 10. Sn equals to n plus 1. So how do you build 2? Okay, actually it's 1 plus 1. How do you build 3? Actually it's 2 plus 1. How do you build 4? Actually it's 3 plus 1. Okay. So, but we also know that 2 plus 2 is 4, right? So you can prove 2 plus 2 equal to 4 using this axiom. Because 2 plus 2 equals to 4 is not by definition. Okay. So definition is the n plus 1 number comes from n. That's all. But why 2 plus 2 equals to 4? You need to use the axiom to play around, to add up 4. Okay? Okay, we will show this next lecture. And then if any problem, just email or put up in the chat. And then we'll see you next week.